In Year 1, we learnt that Ze isomers were molecules that had the same structural formulae, but the arrangement of the atoms was different. Ze isomerism was said to be a form of stereoisomerism. We are now going to cover another form of stereoisomerism, which is called optical isomerism. First, let's consider a pair of hands. Each hand might be considered the same. However, a right glove will not fit properly on a left hand. Some molecules show a similar phenomena. Let's think about a carbon atom that is bonded to 4 different groups. Imagine this molecule was sat on a mat with allocated spaces for the iodine, chlorine and bromine atoms. Now let's consider a molecule that is the mirror image to this molecule. If we try to place that mirror image on the allocated spaces for the iodine, chlorine and bromine atoms, we are not able to, no matter how we twist and turn the molecule. So although the two molecules would undergo the same chemical reactions, as they have the same functional groups, they are, like a pair of hands, not identical. Carbon atoms within a molecule with 4 different groups attached are said to be chiral centres. Nitrogen atoms with 3 different groups attached, because of the lone pair, also act as chiral centres. A molecule with a chiral centre and its mirror image are called a pair of enantiomers. Although a pair of enantiomers may undergo the same chemical reactions, they may interact differently with biological systems, and it is not unusual for drug molecules that are optically active to have one enantiomer that is effective in the treatment of a condition, and another that is either ineffective or might cause harm to the body. The term optical isomer comes from the phenomena that a single pure enantiomer in solution will rotate plane polarized light. If the enantiomer rotates plane polarized light in a clockwise direction, the isomer is given the plus prefix in its name, and if it rotates light in an anti-clockwise direction, it is given the minus prefix. A 50-50 mixture of each enantiomer is called a racemic mixture. A solution of racemic mixture will not rotate plane polarized light, as the contributions from each enantiomer on the polarized light cancel. By merely inspecting the chemical structure of an optically active compound, it is not possible to assign it plus or minus. This has to be done experimentally. You need to be able to draw a pair of enantiomers. For the 2 enantiomers of the amino acid alanine, we will start with the carbon that forms the chiral centre. We will then draw 2 bonds which are solid single thickness lines that represent the bonds in the plane of the paper / screen. We will then draw a bond coming out of the screen towards us as a solid wedge, and a bond going away from us as a dotted line. This is a tetrahedral arrangement, and we covered this in Year 1. We will now add on 4 different groups to each of the bonds. Now we need to draw its mirror image. We again start with the chiral carbon, and then draw the 2 bonds in the plane of the screen, but the diagonal one going in the opposite direction. We do the same for the other 2 bonds. We can check because 3 of the pairs of bonds should cross if they are continued and should not run parallel to each other. We then must make sure we place the 4 different groups on the correct bonds. You will need to be able to identify chiral centres within a molecule. This is the structure of the female hormone estradiol. What we are looking for are carbon atoms with 4 different groups. In a skeletal structure like this, it may be helpful to draw on the implied hydrogens. In this molecule, there are 5 chiral centres. Chiral centres are often shown with an asterisk.